Well, thank you everyone for coming. It is my honor to be here. I'd like to thank Dr. Sosa and Dr. Bravo for extending the invitation for me to come down and speak with you today. I actually love doing this kind of thing. As you can tell, I'm going to give this talk in English. My Spanish is worse than you can imagine, so I'll just pass on that. And I got strict orders to keep it to an hour, so I got my clock going here. And the other thing I would say is I'm an old college professor. If you have questions as I'm speaking, feel free to stop me and ask a question. I know we have questions at the end, but questions during the middle don't really bother me that much. I was asked to come up and speak on the work that we do up in the U.S. on atmospheric deposition. And for those of you who are not air pollution people on a day-to-day basis like I am, what we're going to talk about today is the flow of atmospheric pollutants into the ecosystem. That's really all we're doing. I must say I had an interesting trip here last night. I didn't get here until about 8 o'clock this morning, but as we were driving in from the airport, we came over a rise and looked down into the valley. And you know better than I do that during the summer, Mexico City has quite an air pollution problem, generally called photochemistry. Lots of sulfates and nitrates and hydrocarbons. Well, I think you all know, even if you're not an atmospheric science person, that when it rains in the afternoon, like if it rains this afternoon, it's going to wash some of that pollution out of the atmosphere, and that pollution is going to go into the ecosphere. And so people look at the job that we do, and Dr. Bravo studies, and Dr. Sosa studies, and their group studies as an atmospheric issue. Well, it is to a certain degree, but it's really input to ecosystem sciences. So if you're a hydrologist, this should be important to you. If you're an ecologist or a groundwater specialist, this is the story of how we track air pollution moving from the atmosphere to the biosphere in the U.S. Just going to go through 3 things through the talk. We give you an introduction to the National Atmospheric Deposition Program, which is the program that I run. Really, we do the monitoring, we do the tracking of that pollution movement. And I'll tell you how we work. And quite honestly, the NADP is very similar to the network that you have here in Mexico that Dr. Bravo and Dr. Sosa run. We capture precipitation before it hits the ground and look at it chemically. And I'll walk through how we do that. I'm going to show you some results. And the joke is, in the U.S., I'm going to show you some results today that even politicians can understand. Very clear results of what we're monitoring. All the politicians left the room, right? I hope. And then I'm going to give you some new directions that we're going within NADP that you as a group here, or as a research effort here in Mexico, may want to join with us in. Some things that we think are important to be doing next, and that I think Mexico should consider. And then I'll do some comparisons about what we're finding in the U.S. and what you're finding here in Mexico at the end. So, the first question is, what exactly is the National Atmospheric Deposition Program? We are probably the oldest atmospheric deposition monitoring group in the world that's still going. We are officially a cooperative research program based at the University of Illinois. That's why my byline is the University of Illinois. I'm a research professor at U of I, south of Chicago by about 150 kilometers. And our program is based there, it's managed there. We measure the wet deposition of pollutants. Again, pollution moving from the atmosphere to the ecosystem in rain. We work all over North America. We have sites in Canada, U.S. We now have a new site in South America, and we have another site in Asia, which we can talk about if you wish. And we have studied and cataloged approximately 450,000 precipitation samples now because this program's been running since 1978. And I would say that predates half of the people in this audience. Next year will be our 40th year. And we're colloquially known as the Atmospheric Rain Network because this project got started with acid rain issue in the 60s and 70s. And so I'll talk a little bit about that. The NADP has one goal and one goal only, and that's to monitor the chemistry of precipitation, which is both rain and snow, and in the atmosphere as consistently and as accurately as we can for as long a period as we can to determine if the conditions are getting better or if the conditions are getting worse. And NADP, probably like many of you do, we are just scientists. We say here are the measurements. When the political arguments start, we shut up. We don't get involved in the political end of it. We just provide the data and tell people what it means. The NADP, most people think is one network. It's actually 5 networks. And we do actually both wet deposition, so deposition with precipitation, and dry deposition, pollutants that actually fall out of the atmosphere on their own, both of which can be important. The main network that most people know of is the National Trends Network. That's the big one that's been running for 40 years. And that does the general chemistry, the photochemistry of the atmosphere, measures photochemistry. We have the Atmospheric Integrated Research and Monitoring Network, or AIRMON. That's a small version of the NTN that makes a measurement of precipitation every time it rains. That network is very small because that's a very expensive network to run. It's very scientifically intensive, but we have some data from that network. The network that I'm most involved in is the Mercury Deposition Network. We have a network that specifically looks for mercury in precipitation. On the dry side, we have the Atmospheric Mercury Network, in partnership with the MDN, measures total deposition of mercury, both wet and dry. We have an ammonia monitoring network where we measure ammonia in the atmosphere, and this is one area I might suggest Mexico get more serious about. Ammonia is a huge issue in the atmosphere now, and we use that to do dry deposition of ammonia plus the NTN ammonium networks. Then we can estimate total ammonium or nitrogen, reduced nitrogen deposition. And then, as I like to say, our first cousin is a program called CASNET, Clean Air Status and Trends Network. That's an EPA network that measures all the gases that we measure in wet deposition, but they measure it in the gaseous form and estimate dry deposition. So the CASNET plus the NTN gives us dry deposition of all of the fundamental air pollutants. So that's how NADP is organized. Here is a distribution over North America for all 5 of our networks. You need to use the key, but the silver boxes, that's the NTN, that's the big network of general chemistry, wet deposition, and that's what I'm going to spend most of the time on today. And as you note, we also have sites up in Alaska. We have had them in Hawaii in the past, although they're not operating anymore, and we've got them up in Canada also. And again, that network is very similar to the network that's running here with Dr. Bravo and Dr. Sosa's group from Mexico. So that big network, what do we measure? We make 1 week integrated precipitation samples. Basically, all the precipitation that occurs in 1 week, it's integrated into one sample. And we look at that precipitation and we look for acid, or H+. We measure the conductivity of the precipitation. We measure sulfate, nitrate, and ammonium, the big 3, as we like to say. Sodium, chloride, and a few cations, calcium, potassium, magnesium, and orthophosphate. And in those compounds, you cover most of the chemicals that you find in the atmosphere. Most of them, not all of them, but the big players, at least in photochemistry. And so again, if I would go back to that rise over Mexico City and I looked at that beautiful cloud you have there at 9 o'clock in the morning, the overwhelming majority of that cloud is going to be sulfur, nitrate, ammonia, hydrocarbons, which we don't measure, but a few other things. We produce scientifically valid concentrations on a weekly basis and deposition or flux. How much moved from the atmosphere down to the biosphere, and we do it for the U.S. and Canada, and it's been running since 1978. There's the NTN networks, all by themselves. As you'll note, we have a few along the Mexican border, and I'll use some of those to compare to in just a little while, but we also make measurements in Puerto Rico, Virgin Islands, up in Alaska, and we're trying to work with a few scientists in Cuba. So we should probably talk about that sometime. And we've been working with Dr. Bravo and Dr. Sosa for years. How long have we known each other? Longer than you'd care to remember. But anyway. There's the second, the Airmon network. Basically, this is just a copy of the NTN, but it takes a sample every time it rains. And with that information, you can do back trajectory work, or you can get much better on zeroing out on what are the sources of those pollutants. But again, that's a very small network in our world. It's only 6 sites. The third network, the ammonia monitoring network, the AMON, the one that I suggested you guys might want to think about. We measure atmospheric concentrations of ammonia using passive devices. I don't know if you've ever used passive devices, but no electricity needed. And so you can use these devices really anywhere. We make gaseous concentration measurements over a 2-week period. Those collectors come back to the lab and they run for ammonia gas, and we can estimate dry deposition of ammonia from those observations. There's the ammonia sites across North America. We have approximately 95 of those running on a week-to-week basis, including Puerto Rico and a couple in Alaska. And this is the reason why we measure ammonia in the U.S. For those of you not in the air quality business, ammonia comes from agriculture. Confined animal feeding operations, fertilizer use. We use hundreds of millions of tons of fertilizer in the U.S. And as I'll show you in just a bit, in our results, we're seeing this ammonia impact on the chemistry of the atmosphere. And I don't know Mexico certainly as well as the U.S., but I'm pretty sure you have farmers here. I'm pretty sure you have farmers that want to make money here, so they're probably using fertilizer. Mexico is industrializing, so you're probably eating a lot more meat, and you're probably producing a lot more of your own meat. So I would be willing to bet that you're developing quite an ammonia problem along with the U.S. and Canada and the rest of the world. The networks for mercury, I'm not really going to talk much about those today. If there's any interest in the audience about mercury, I'm happy to talk to you about it. But just like the NTN network, that basic chemistry wet deposition network on the left, we have the mercury deposition network where we integrate all the precipitation over a week and measure that sample for mercury concentration and flux or deposition down to the ground. Use a similar sampler there, and then we have the gaseous version over on the left where we actually do mercury dry deposition measurements. And one thing I never can say enough, all of our data, every bit of it, is available on the web. You can download it this afternoon if you so choose, and I'll show you how to get all that data in just a bit. This is the distribution of our mercury network. Again, like most networks, they're in the east where the population is, but we have a few down south. And there's our one site in Taiwan, Asia, and we have a site running in Hawaii also. So that's what we do and how we do it. This is the who of the NADP, and this is one of the real advantages that makes NADP so valuable, in my opinion. We have a lot of funders. We have universities, we have federal agencies, we have state agencies, tribal agencies, and other organizations. And so we are extremely well diversified in funding. And if somebody pulls out 1 year, it's not the end of the world. It's only a small percentage of our funding. And so with that diversity, we've been able to keep going for quite a long time. We have 8 major federal agencies. I'm sure most of you know most of them. USGS and the National Park Service and EPA are the primary funders of our network on the federal level. We receive funding from 30 different states. As you probably know, each state has its own environmental network. A lot of universities in the U.S., each tribe is responsible for its own air quality, and they have their own air quality professionals, and so tribes join with us to do this kind of monitoring. Researchers at universities like myself, from one end of the country to the other, and then we also have a few power companies that contribute money, and the Environment Canada is a member of NADP. So we're really a big monitoring cooperative that everybody makes the same measurement at the place that they want the information, and we bind together by laboratory services involved, and we do everything the same way. So as we say in the U.S., the results are apples and apples. I know in your network, every network site does it the exact same way, so they intercompare well. The same thing happens with NADP. Everybody at all 250 sites does it the exact same way every Tuesday, or at least we hope. But that's the way it's supposed to go. The organization has basically, I have a board of directors. It's the executive committee in red. That's made up of the people that fund the network. If you fund the network, you're part of the executive committee, you get to help make decisions. And then the other side of NADP is the operating arm, which I call the program office, and that's what I run. The board of directors makes the decisions, they tell me what the decisions are, and I carry them out. Pretty simple and straightforward. We're a monitoring cooperative. We have lots of QA. I don't want to bore you to death with QA. QA bores me to death. It's important, but you know what I mean. But we have standard protocols for everything. Operations, data handling, review of the data, how the committees operate. It's all written down and we try to follow it. We do schedule blanks and spikes throughout all the labs. We continually intercompare the labs between them to make sure that they are performing at the level that we expect them to. We compare the labs to international labs and make sure that everybody's getting the same answer. We have independent outside groups that come in and review us on a regular basis, and so we're pretty proud of the QA. But it's really important because we don't really have anything else to sell except our reputation. People fund NADP because we produce good data. If we didn't produce good data with this QA system in place, nobody would fund us. So it's a necessary evil, unfortunately, for all you lab people out there. I usually throw this out too. Why does NADP survive and why it survives so long? The most important one, I think, is we have dedicated operators. For all of you people that do field work on a regular basis, you know that it really boils down to the person that gets up on a Tuesday morning and goes out to the field site when it's 104 degrees and makes the sample happen. We have a very good set of dedicated operators. But we have common protocols that we all agreed on. We have a cost-effective design. We use one laboratory for all of our samples, so QA is relatively simple. And we have a commitment to long-term monitoring. Some of these organizations have been contributing money to NADP for the entire 40 years of our existence. And that is the hard one. You have to get the people with the funds and the want to have the information to commit long-term. Because you've got to do monitoring for long-term if you're going to tell if things are getting better or if things are getting worse. How you do that? Can't help you there. But you get my understanding. And the other valuable thing about NADP is we release our data, and over the last 6 years, about 1,000 journal articles have used our data. We always have it's always a tough argument to make to people to release their data, but that's a hard and fast rule within the NADP. In the US, it's considered public information. So all the data is on the web as soon as we can get it there. And it's contributed to at least 1,000 articles in the last 6 years. And those are the ones that I've been able to find. There's probably other reports out there. And so we are big believers in releasing data unrestricted. We tell people what's valid and what's invalid, and we give it all to them. We tell them, we recommend they don't use the invalid data, but if they want to, they can. It's all out there. So, where do we measure wet deposition? I think you've seen basically this map already all over the place, from one end of the country to the other, but I want you to focus on the red dots. The red dots have all been monitored for at least 30 years. And at the core of that red dot network is the USDA. Because believe it or not, USDA was concerned that acid rain was affecting the yield of plants and the yield of the U.S. agricultural industry back in the 70s. And so the USDA is at the core of this network. And they have most of the long-running sites. Again, and some of those sites will be 40 years running. We probably have about 20 sites that have been running for 40 years. Yes, sir?
Just excuse me. I was wondering if you have a rain gauge co-located with your air quality measurements, air quality equipment.
We do. We have a wet deposition collector and a rain gauge. We use digital rain gauges, and we test them before we allow them in the network. And we have selected 2 that we've been using over the last 8 years. And there's some paperwork floating around that'll tell you exactly which gauges we use. But yes, we spent a long time making sure that they work as good as the manufacturers say they do. And I've got some pictures that'll show you. There we go. These are our collectors. Now see, these are some of the older collectors, but this is just sort of random pictures from around the network. Penn State, which is Pennsylvania. We measure down in the Everglades. We measure at Colorado at about 4,000 meters, and that's a very difficult sample to get. It's about a 3-hour trip in on a snowmobile in the winter every Tuesday to get that sample. That platform is 17 feet off the ground, and it's all the way up with snow in the winter. We measure this is Niwot Ridge in Colorado, where it snows when the wind's blowing about 50 kilometers an hour. So that's a very difficult sample to collect too. We measure in Alert, Canada, which is about as far north in Canada as you can get. We measure where it doesn't rain, in the middle of the desert in the U.S. And that's central Illinois on the right, Bonneville, that's where I live, where it's nice and flat, and we get maybe 40 inches of rain a year. We measure in the cities. There's a picture of the New York City measurements and rural Washington, D.C. And just a great picture here. Everybody should get a good dog when they start a site. I think that's rural Pennsylvania, actually. But we measure from one end of the U.S. to the other, including Alaska. How do pollutants get in the rain? I think we talked a little bit about that earlier. Pollutants get emitted from a number of different sources. And if you're living in Mexico City, those big sources are primarily automobiles, power generation, probably fertilizer use out in the country that moves in, but vehicles and power generation, basically the urban 21st century environment is what is creating pollution in the atmosphere. But that pollution can get caught up as the clouds actually form, and we call that rainout, or the pollutants can get washed out as the rain falls through the pollutant layer. Either way, you can end up with wet deposition of pollutants. And all we do is put a little sampler down there at the bottom and capture that precipitation before it hits the ground and gets dirty. and then we look at it chemically, and you can tell a lot by how much is coming out of the atmosphere of each individual pollutant. I won't bore you with the math necessarily, but we know with our rain gauge how much rain came down. We know by the concentration that came out of the laboratory how much sulfur, or sulfate, I should say, is in the sample. We do the math correct for the units, and we end up with micrograms or milligrams of sulfate per week flowing through 1 square meter of ground. And that's our flux, and that's the information we put out. And the same is true for the Mexican network. There are other types of depositional processes. We've been talking about wet deposition, and we've been talking a little bit about dry deposition. You all know what dry deposition is. All you have to do is go look at your windowsill, and you clean your windowsill on a Tuesday, you come back on the next Tuesday, it's dirty again. That's pollution essentially falling out of the atmosphere, dust, solid particles. It's the same thing. That's all dry deposition is. It's very difficult to measure, but you can estimate it using models, and that's how we do it. But I want you to think on top of this. There's something called through fall. Imagine you're out in a forest, walking through a forest, and that forest is at the pollution cloud level, where the pollution cloud from Mexico City moves through the forest. It's going to basically move pollutant to the outside of the trees, and when you wash it off with rain, you're going to have what's called through fall, the pollution washing off of the leaves and the twigs and the bark of the plant, of the canopy, down to the ground. It's not really dry deposition, it's not really wet deposition, it's in between. And so some people make measurements of through fall, and this is the one that's important in some situations. If you have pollutant on the outside of a leaf, and during the autumn when that leaf falls off, that pollution is moving from the atmosphere down to the ground. And you can add a lot of pollutants just in the fall by putting leaves into a lake system. And we are making measurements of litter fall of mercury in the U.S. And believe it or not, some of the litter fall fluxes are higher than the wet deposition. And it might be we've been measuring the wrong thing for 15 years. That the mercury that's coming off with the litter fall in the autumn is more important than what's going on all year with the rain. So another area that Mexico could potentially go in. And then when you talk about deposition, you always have to adjust for how much goes back up into the atmosphere, called re-emission. If the pollutant's in the appropriate chemical form, it can volatilize and go right back to the atmosphere. And so it's not net deposited, as we talked about. So when you're doing nitrogen or sulfur balances, you have to worry about re-emission too. So, enough of the boring stuff. What do we know? What do we see? Well, here's one thing we see, and I hear all the time. Well, acid rain's not an issue. We took care of that in the 70s. Well, that's not exactly quite right. Acid rain's a whole lot better than it was in the 70s, and we have data to prove that, but it's still an issue. Everything below, when a precipitation has a pH of 5.1 or less, it's considered acidic rain. And if you look at the entire eastern part of the U.S., this is the typical pH you find. We still find pHs 4.7, 4.8, 4.9. Now, when I was in college a couple of thousand years ago, the typical pHs in the eastern U.S. 4, 4.1, 4.2. So it's gotten a whole lot better, but it's still an issue. The frequency of precipitation as measured in 2009, again, this is straight from our data. If you look over to the east, at least half the time when you capture a precipitation sample, it's going to be more acidic than it should be. So again, it's a much better than it used to be, because again, when I was in college, it was more like 80 or 90% of the time the precipitation had a pH less than 5.1. Now it's in the 50s, but it's still an issue. It's still a problem that we've been working on for 40 years. This is trends in emissions, and we were talking about emissions inventories this morning, you can see dramatic fall off of sulfur dioxide emission in red and nitrogen oxide emissions in blue, and those are the drivers. That's the gases that come out of the tailpipes that drive the photochemistry equations. We've limited emissions of sulfur by almost 90% over the last 35 years. And we've limited the emission of NOx, or NOx, by probably 60% over the last 30 years. And our network was put in place to see if that had the appropriate effect. Are we getting where we need to? Okay, so I'm going to show you my first animation here. This is pH over time. So you're going to see a map of the U.S. pH over time. This is pH deposition, or hydrogen ion concentration, in 3-year running averages. So each map will represent a year, but it's actually a measure. It's an average of the 3 years, of the 2 years on either side of it, plus that year, to sort of smooth out some of the bumps. And I want you to tell me if you can't see this change. Give me a second here. All right. So again, this is hydrogen ion deposition across the U.S. over the past 20-something years. And we're moving in time. There's year down at the bottom. We're into the early 90s, and now the Clean Air Acts are beginning to take hold. And red is low pH, green is high pH using the color scale. 2003, 2004, 5, 6, 7, 8, 11. And I was joking earlier about the results that even politicians can understand. This is what you get with a long-term measurement. An argument that is this convincing. And I'm going to, since I started you guys on this one, I'm going to run it again, just so you can see it one more time. So we're looking at pH deposition from the middle 80s, before the Clean Air Acts really started going, until the current times. And what you want to focus on is that red blob, low pH, in the industrial center of the U.S. And it's slowly, but slowly, is going away. And that is a direct result of the restriction of sulfur dioxide emission. Sulfur dioxide in the atmosphere with water in place is going to produce sulfuric acid. That's where acid rain comes from. NOx, nitrogen oxide in the atmosphere in the presence of water and a few other things, is going to give you nitric acid. Again, driving this acid rain issue. And if you restrict, I think it is very clear in the U.S. that if you restrict sulfur dioxide emission and nitrogen oxide emission, that you can clear up the pH problem that we had in our rainfall. Yes, sir?
Didn't you have similar problems in the West Coast?
One more time.
Didn't you have the same problem in the West Coast? Because I see that the West Coast is pretty green.
Well, his question is, why is it so green out west?
Right.
The West never had much of an issue with acid rain. They typically had very acidic fogs along the coast, but the pHs of rain were never much below 4.9, even in the cities. It's an East Coast issue because most of the sulfur emission points in the U.S. are in the east, and you have a lot more water in the atmosphere, and you have to have those two things to make sulfuric acid. And the acid rain problem is primarily driven by sulfuric acid. That's changing though, and I've got another slide to tell you, but that's why it's so green out west. All right, so back to my general presentation. You'll have to forgive me, I'm not talented enough to be able to embed my This is, so we looked at the hydrogen ion animation. Now we're going to look at sulfur deposition, deposition of sulfate, the other side of that acid compound. And I can bet you can guess what it's going to look like. Same years, same idea. Red is high concentration, high deposition. Green is low deposition. And you can see out west, there's not a whole lot of sulfate happening out west. But again, you can see the sulfate.
In that for the power to the use of coal,
Where does sulfur come from? Sulfur comes from coal combustion primarily. There is sulfur in natural gas and gasoline, but the biggest source of sulfur in the atmosphere is from coal. It's a contaminated coal. I'm sorry. I make the assumption that you guys are all atmospheric people. Sulfur, dirty coal. And in the U.S., we have two reserves of coal, one in West Virginia, that Appalachia, high sulfur coal, and in Wyoming, the Rocky Mountains, which is low sulfur coal. And part of the restriction is, or part of the reaction industry had to the sulfur problem was to switch from eastern coal to western coal because half of the sulfur came out when it showed up at the mine, or it showed up at the, that was one way they dealt with it. Very little coal is coming out of West Virginia anymore. It's being chucked in by the trainload for Wyoming. But you guys see that? The sulfur issue went away. It didn't go away, but it's a whole lot better than it used to be. Let me run it one more time. So this is sulfur flux to the surface in the U.S. from the mid-'80s through their current times. And the amount of sulfur in rainfall is going down by a factor of 5, 10, huge amount of reduction. And it's restriction of the source of sulfur dioxide. Now, I haven't done any chemical analysis on the plume in downtown Mexico City, but I'd be willing to bet there's plenty of sulfur in it. Coal-fired power, I guess. All right, so I mentioned this a little bit later, the idea that sulfur dioxide and sulfuric acid was driving an acid rain issue. Maybe we change it. So I'm going to show you one more animation, and this is nitrogen deposition. So this is a combination of nitrogen oxides in the atmosphere with rain. It's called nitric acid and ammonium combined. And this is deposition from the atmosphere to the ecosystems of nitrogen by itself. Early mid-'80s. And this cloud, or this flux of nitrogen, is actually going the other way. It's actually growing, getting larger. And the trick to understanding why it's getting larger is to know geography of the U.S. This is where I live, so that's important for y'all to know. This is the agricultural breadbasket of the U.S. Oklahoma, Missouri, Iowa, Illinois, Wisconsin, Minnesota. That's where we grow all corn. That's where they have all the pigs and cows, because now we don't feed them grass anymore, we feed them corn. That's where we use all the anhydrous ammonium to make the corn grow better and taller and faster so we can feed more cows to eat more meat. And it's harder to tell, but what's going on is when I was in high school, and you guys weren't born, the issue of acid rain was sulfuric acid driven. It was sulfur. Now the sulfur has been regulated out of the atmospheric system, and the problem is nitrogen. When people come to our meetings now, hardly anybody even mentions sulfur. They're all focused on nitrogen and the explosion, not of nitrate. NOx plus water plus sunlight gives you nitrate, nitric acid, but they're focused on ammonia. Wet deposition of ammonia gas or ammonia. And this is the reason why. It's exploding while sulfur is going away. And it's shifting in location. It's shifting from the industrial center out into the agricultural center. And the funny thing, or at least I kind of think it's funny, in the U.S., USDA was always rah, NADP does great things because it's protecting the food source. Well, now, USDA has a target on their back because they're the source of the nitrogen gases. And they don't think they like us as much anymore. Imagine that. But anyway, it's a shift from sulfur, high sulfur coal creating the problem. That's been regulated away, and now it's nitrogen oxides from combusting anything, any kind of fuel, phones, to produce electricity for phones and cars and all the stuff that we all want, and agriculture, moving from a grain society to a meat society, and how we do it in the U.S. in the industrial processes. We use a lot of nitrogen, and the excess is moving into the atmosphere. And so that's sort of the big result from NADP. Back into animations here. Here's a nice little slide I put together. If you know chemistry at all, this map is in microequivalents per liter. Think of it as charges, moles of chemical charges. And sulfate, SO4 2- has 2 equilibrium charges, and nitrogen has 1. And this is a ratio between sulfur equilibrium back in 1984 versus what it looks like today. If you see red or orange on this map, that chemical map is driven by sulfate. There's more sulfate contributing to the sample than there is nitrate or ammonia. That's what it looked like in 84, 85, 86, dominated by sulfur. This is what it looks like now. Blue is nitrogen dominated. All the way through about these last 2 colors. We've got a couple of spots that are still dominated by sulfur, but the rest of the country is all nitrogen driven now. And so again, we've had a shift in constituents from sulfur to nitrogen. We've had the addition of ammonia. It's changed location in the country. Now it's in the middle of the country versus where it used to be in the industrial Midwest. And it's different chemistry. It's not creating nearly the same problems, it's creating different problems. So by regulating away the big problem, now we've got other problems that come into focus, if that makes sense. And I would expect the same thing is going on in Mexico. So, some new directions and some comparisons. Just to wrap up. We use a highly defined precipitation grid now to do much more accurate, we think, deposition maps. The precipitation layer, if you're a GIS map maker, that gets multiplied through by the analytical concentrations to make our deposition maps. We use 9,000 rain gauges now. It's something called PRISM, and I can't tell you what PRISM stands for, but it's the official definition of how much it rains in the U.S. as defined by USDA. And they gather all the gauges that they have confidence in, build a data set, and let that data set out to use. And so now we use that. So we're making much more detailed maps than we used to, just based on more precipitation data. So that's one thing that's kind of cool and new. We've also added bromide. We've traditionally measured sodium and chloride, et cetera, but now we've added bromide because a lot of people think that we should be seeing it in our samples because they use it industrially, and they also use it as a defoliant in the grass industry in California to make grass for suburbs. They go out to California, plant grass, or before they plant grass, they use methyl bromide to kill everything in the soil. Then they plant grass so it doesn't have weeds in it. And so we thought if we added bromide, wet deposition bromide, we'd see huge spikes. Well, this map just says we got a lot of non-detects. So there's not a lot of bromide around, but we've added it to our suite and we do it on a regular basis. And if it starts to pop up as an issue, we'll at least see it. Something else that you guys might be interested in, critical loads of atmospheric deposition. A critical load, for those of you who don't know the lingo, is if you add a specific chemical compound to an ecosystem, how much of that compound can you add before you change the system? That's a critical load. If you add more nitrogen to a system, you'll begin to change the species balance. That's an impact. Or you'd be able to start to change the chemistry of the lake or the river. That's an impact. And that's looking at regulation from a critical load standpoint. And again, we don't do regulation, but we have a new committee that looks at the world through critical loads lens. How much sulfur can you add to this ecosystem in this particular location without changing that ecosystem in any way? And they like to think it's a new way to regulate. Politically, I don't think it has a chance, at least not for the next 20 years, but scientists are beginning to think about it that way, and they're beginning to make really cool maps. For example, how much sulfur and nitrogen can you add to a system over the U.S. before you start to change that system in some fundamental way? And they're beginning to make deposition maps. And so it's a logical next step. Since we measured the deposition of sulfur and nitrogen, they are looking at our information to say, okay, are you putting more into that national park than can actually be put in there without changing the national park? Because the national park is required to keep the system as it is. Does that make sense of how they think about it? It's sort of turning regulation on its head. What can you add without changing it? And that's all we want to add to the system. And that's what this critical loads subcommittee or science committee of NADP does. And it's an interesting idea. And it's something that you might want to think about doing here in Mexico. We've got lots of these maps. This is how much can you add to a surface water of sulfur and nitrogen. The other one was for forests. They play a lot of those kind of games. We also have another group called Total Deposition. And their goal is to make NADP more of a total depositional organization. For 40 years, we've measured wet deposition, and we do it pretty well. But that's only part of this story. Dry deposition and potentially through-fall and litter-fall all go into the sum of deposition. This committee looks specifically at how do we move beyond just the wet deposition to total deposition, because the critical loads people need all the nitrogen coming in. They don't care if it comes with rain or comes in dry. They need to know how much is coming in total. And so that's sort of another direction, and they love making maps too. This is dry deposition of nitrogen estimated from gaseous concentrations, very spotty, but this map sort of really tells the tale. How much of the total deposition is dry deposition, meaning we miss it within the NADP networks. And if you look out in California and Nevada, the estimate is 90% of the nitrogen is coming down as dry deposition, not wet deposition, which means we never even see it. So we're missing 90% of the story. And it goes throughout the rest of the U.S. These are model estimates based on very limited data, but it's a first step in trying to estimate dry deposition of these common pollutants that we look at so specifically in wet deposition. I've got 10 minutes left. We make measurements down in Argentina. Dr. Enrique Bouchard at the University of Cordoba Just wanted to show you a quick estimate of what we're seeing. So, the stem and whisker plots are average concentrations for sulfate that we see at all these sites down here in red in the U.S. So if you average out all these sites, this is what it looks like over time. Mean, or median I should say, 25, 75%, percentile 95 to 95. That's our general, what we see in the U.S. And these red dots are what they're measuring in Argentina. Some high, some low. So I'd say they're bouncing all around, a lot more than our observations bounce, and sometimes they're extremely high, sometimes they're extremely low. So they've got to figure out what the sources are down in Argentina. But this is the interesting one. This is nitrate. Again, if you look at this one in the blue dots, in almost every case, they're higher than our typical distribution. They're on the high side of our distribution. So they've got a lot of nitrate going through their system that they've only begun to even measure. Much higher in nitrate than we were seeing in, again, southern sites that are kind of, sort of comparable. And then this is for ammonium. Again, same story. Much higher concentrations of ammonium in wet deposition than we're seeing. And we think we have a big problem. So I would say the same thing there. And if I could just wrap up, I threw in a few comparisons to data from year 2 sites. I hope you guys don't mind. This is the Mexico network. As I understand it, 12 sites, a lot along Veracruz. And please, you guys jump in if I screw up. And some out in the Yucatan, and then several measurements made here, I believe, at UNAM. And what I tried to do is find a comparable site in the U.S. to some of the information that I had from here in Mexico. And to do that, I had to screw up the graphics. So what I tried to do is line up the years. So this is the UNAM measurements in years. And then this is the nearest NADP site that I could find that was kind of comparable. And I stretched it so the years would line up. So you ought to be able to compare this to that. And what I see here, this is the most south site I have in Texas. It's in Victoria, Texas, if you guys know Victoria. And then this is out on the Gulf. And it's not exactly the same, but it's in the same neighborhood. So I would say this shows you guys have really good chemistry going on. You're not way far from what we are. You're fairly consistent with what we are. Not necessarily the same trends, but generally speaking, I would say the pH and the sulfur concentration, the pH, is generally rising from about 2006 to 2007. So I would say the two networks across the border compare fairly well. Based simply on this, it's not apples to apples, certainly. You have different sources down here than we have. But I would say, for all practical purposes, we see the same general thing in South Texas that you're seeing on this side of the border, along the Gulf. I compared it to basically a site outside of Miami, thinking it was more maritime, hot, and basically I would say generally the same thing, the same general trends. The pH is going up, and that's certainly the right direction. And so again, I would say across the Gulf, from one network to the other, they're generally following each other. So I would say we complement each other quite nicely. Again, please don't beat me up. It's not apples to apples, I understand, but this is as good as I can do in a pinch. And this is Dr. Bravo's graph. This is pH in Mexico City, from blue being about 7 to orange being about 4.5. So very basic, to very acidic, and years in each block. And you can tell over the years, at least in Mexico City, Dr. Bravo is seeing from the network, I would say, a heavier or a larger increase in pH particularly on the south side of the city. I'm not sure why that is. I'm sure someone in the audience certainly does. But then I compared it to Houston. We have a site near Houston, and I tried to stretch the color bar so you could kind of compare colors, if you will. We're seeing in Houston, we're seeing generally this color, whatever that color is, burnt yellow. You get the idea. So what I see in this comparison between Mexico City and what little data I provided from Houston is pHs in rainfall around Mexico City that are much more variable than what we see in Houston. From very acidic to very basic. I'm going to guess the very basic comes in when a lot of dust blows in from the desert and starts to satisfy bonds, but I don't know that. But we're much less variable in Houston. Again, it's just one comparison. Whereas you see, at least from this graphic, a lot more variability in pH in Mexico City. And again, that's Dr. Bravo's work and Dr. Slessor. So with that, I'm going to shut up. And I still have 3 minutes. Not bad, huh? I just wanted to point out to you that that web address, and really the front end is all you need if you're interested in the NADP data. If you want to compare across the board or see what we're measuring, all of our data is there. The good stuff and the bad, and it's clearly marked what's good and what's invalid. But if you go to nadp.isws.illinois.edu, you can get access to every bit of data we have, to all of our SOPs. You can complain about the way we do it. You can use our data, anything you want. And again, the reason why we do that is because our job is to support research. That's what USDA pays us for. And if people don't use our data, we're not supporting research. And so as a research group with quite wide-ranging interests, if you have a use for our information, I know it's not necessarily in the area you're working in, but if you've got any use for the data, please feel free. It is free. Absolutely free. So with that, entertaining questions?